Hi, it's a pleasure to have Todd. He's going to talk about presenting quantitative inequational theories.
Okay, yeah, thank you so much. And thank you to the organizers. I don't know if you've been able to tell, but I've been having an excellent time. I won't go into details on camera. What I want to talk to you about today is some work that's kind of peripheral to my main line of research. I'll talk about my main line of research in a second. And also the title is a little bit misleading. It should be presenting with quantitative inequational theories, but I won't split hairs. Okay, so let me actually tell you about the motivation. So the motivation is that last year, me and some co-authors worked out a nice recipe for building sort of algebraic, okay, I'm going to say it this way, algebraic accounts of processes. In other words, programming languages, sort of in the abstract. And the format of the processes is that, okay, well, they're state-based processes. And the idea is that you have some, I'll use this, so a set of states, these are given by the circles here, and a function which takes the states to some formal combination of weights and labels and states. That's a bit abstract. I mean, you can consider this particular example. So if we replace M with the finitely supported probability distributions, then what we get are, for every state, we have a finitely supported probability distribution on label state pairs. And these are really conveniently denoted with these like transitions that have been labeled with a real number and some label from the action labels. You can imagine this state right here is being, okay, there's a 40% chance I'm going to do A, and then I'm going to go to the top state, and a 30% chance I'm going to do A and go to the bottom state. So they're not deterministic or anything like that. It's like, it's probabilistic. And what's interesting about this particular example that I've written down here, so here I've got finite probability distributions, is that it's contained in a larger functor, the thing that constructs the free module on the non-negative real numbers. And I'm thinking of the non-negative real numbers here as a semi-ring. And if I write down this automaton again, you'll notice that if the states are x, y, and z, I can write down this specification where, okay, on the left-hand side, I have the states, and on the right-hand side, I have formal linear combinations of the label state pairs. Basically, for the rest of this, I'm going to drop the labels because they're not super important. But the point is that I can write down this automaton right here, this process on the right-hand side, using terms from the free module on the non-negative real numbers. Okay, so recently I extended this framework, this recipe, I sort of recontextualized it for partially ordered processes. It's not important that you know exactly what these are, but the point is that this function now is from not just a set of states, but a partially ordered set of states. And this transition function is now monotone. I want to be able to draw pictures like this. So this picture right here was the automaton from before, except I've added in some blue lines denoting a Hasse diagram. So this is a process where the states have a partial order. Okay. Now, I'd really like to be able to write these things down, but the problem is I still got an M here, and it's a bit unaccounted for. Because in order for me to talk about monotonicity, this M not just has to construct the free algebra, but it has to construct the free ordered algebra. And, well, if I want to draw pictures like this, natural question is, okay, well, but what is the free, R plus module that has on a partially ordered set? What is the free ordered algebra now? And, is it the same as before with just a new order? What is the order? These were questions that sort of immediately came to mind now. And of course, because I did answer this question right here, I asked the more general question. If I replace R plus with an arbitrary ordered semi-ring, I'll define this in a second, how do we construct the free ordered semi-ring? And can I construct it basically in a way similar to this one before, where I've sort of took, okay, well, you can obviously do it with free terms. I'll talk about the explicit construction in a second. So let me just tell you what a module over a semiring is, just in case you haven't seen it before. I've sort of written it down as a diagram. Basically, if you start with a semiring, it's a commutative monoid with an action of the semiring on it. You can think of it as like scalars in a vector space, or if you like ring, modules over rings. I mean, it's the same thing. The only difference between semirings and rings is that there's just no subtraction. That's the only thing I'm dropping. Okay, and constructing the free, so if I'm going to fix a semiring now, P, constructing the free P module on a set is actually really sort of straightforward. One way to do it, and the way that was written down before, was it's just a set of all finitely supported functions from your set, here I've called X, into the semiring. There's no structural conditions or anything. X is just a set. And we're just making sure it's finitely supported. A nice picture of this is just sort of bar graphs with finitely many bars. And here I've got the x-axis, the set X, and then the y-axis is just like the values from the semiring. That picture might seem trivial now, but it's not going to be in a second. So what is the defining property of the free P module? This is kind of the basis of what I'm going to be talking about in a second. The defining property is a universal property. It says that for any function from your base set into another P module, that function uniquely extends to the set of all finitely supported functions, such that on Dirac deltas, it takes the values of f. If you like monads, what this is saying is that if you extend the identity function, then this set of functions with the Dirac deltas and this sort of evaluation map, this gives you a monad on the category of sets. If you don't like monads, that's okay. We can still be friends. Okay, so, but what does this look like in an ordered setting now? So an ordered semiring, at least for my purposes, it's going to be a semiring with a partial order structure on it. Okay, that's intuitive. I'm going to require our ordered semirings to be positive. So this means that the additive identity, so the 0 in the commutative monoid, that this is actually at the bottom. This is often called positivity, but I'm going to just not use the word positive. I'm just going to call these ordered semirings. Okay, and yeah, the sort of additional constraint here is that addition and multiplication have to be monotone in both arguments. Okay, and an ordered P module, it's pretty straightforward given the diagram we had before. Basically, all I did was I just replaced all of the objects with partially ordered sets. So it's an ordered commutative monoid, or a commutative ordered monoid, I don't think it matters, and a monotone action of P. So this means it's monotone in both arguments. Monotone in the P argument and also monotone in the commutative monoid argument. Okay, so before I go to the next slide, I just want to say, well, we're getting into the territory now where I'm going to suggest a particular construction of the free ordered P module. And what I'd like to do is sort of bootstrap our construction on sets. So I'd like to take these finitely supported functions because I know how to construct the extended homomorphisms. And I'd like to give that set a partial order that makes the whole thing the free ordered P module. But the question, of course, is what order do you choose? So I scoured the, well, because of the probability example at the beginning, I scoured the ordered probability theory literature, or the ordered statistics, or I think there's another area called social choice theory, I think. I think this is a popular thing in the Netherlands. So I sort of scoured this literature, and there was this very nice order, which was based on upwards closed sets that happened to just be I mean, it seems like it works perfectly. So I'm going to call it something a little different than the literature calls it. Basically, what we care about are values on upward closed sets, or upper sets, I think is a term I've heard a lot in the conference. So an upwards closed set is just one that looks like sort of an upwards cone. Basically, if X is in the set and Y is above X, then Y must also be in the set. So the order this order that I found in the literature is really nice. I've sort of hopefully suggestively called it the heavier higher order. And the idea is that one distribution theta 2 is heavier higher than theta 1 if on upwards closed sets, theta 2 takes a value that is higher than or greater than or equal to the value of theta 1. So theta 2 on this whole upward closed set is greater than or equal to the value of theta 1.
You have u where you have x. You want to put u when you have x.
Yes, sorry. Yeah, these two x's should be used. I think I had x and u. Anyways, sorry. Another way to write it would be like theta 2 of u, big U, is less than or equal to theta, or greater than or equal to theta 1 of big U. And I'm going to just say that theta 1 and theta 2 are equivalent if they're mutually heavy or higher. Now, I'm specifically stating that they're equivalent if they're mutually heavy or higher because in general, this is actually just a preorder. This is not always a partial order. And there will be some important examples where actually it fails to be a partial order. So the bar graph returns. So here I've got two finally supported distributions, orange and blue. If I want to check that orange is heavier or higher than blue, and here I've ordered x sort of left to right. If I want to check that orange is heavier or higher than blue, which it seems like it should be, I just need to look at all of the right-facing rays, and I need to sum up the values of the orange one and just check that it's greater than the sum of the values of the blue one. So this is kind of the picture I have in mind. I'm not only considering linear orders, but I think this is an easy picture to look at. Okay, so my question is this. If I start with the finitely supported functions, and I mod out by the heavier higher order, do I get the free order P module? This is my question. I don't have an answer to this question. I'm going to tell you some cases that I've worked out, sort of the more important cases to me, at least, I've worked out. But it seems like it should be true. It's been very difficult to come up with a counterexample. So let me just remind you of the universal property we need, because it's slightly different in the partially ordered case. In the partially ordered case, we want this. So we replace functions with monotone functions. So the idea is, given any monotone function from a partially ordered set, from your partially ordered set, the one that we're going to generate the free ordered module from, into an ordered P module, we need this monotone function to lift to a unique monotone P module homomorphism. That's just one that preserves the operations and is monotone, which extends the Dirac delta. And here I'm writing delta here, but it's really taking the equivalence classes of the Dirac deltas from before. Okay, so here's what I've shown about this. I've sort of split the class. So I'm trying to determine this, the answer to this question in terms of properties of the P itself, the semi-ring, the ordered semi-ring P. There's some properties of the ordered semi-ring P that actually guarantee that this indeed is the right construction of the free ordered P module. And I'm going to talk about these two individual cases over the next couple slides. So let's talk about the first one, the cancellative indifference ordered case. So I call an ordered semi-ring P cancellative if addition on the right by a fixed element is an order embedding. So basically, if you're given an expression like this, you know R plus T is less than or equal to S plus T, you can peel the T off, and that sort of peeling the T off is monotone. And we say, oh, okay, I'm going to call P difference ordered. This is not my definition. It's from the literature. P is difference ordered if R below S means that you can add something to R to get S. Right? Okay, so what's really nice about this particular case, actually, is that in the cancellative difference, well, okay, in the cancellative case, this heavier higher order is actually a partial order. And so, if you like monads, in the cancellative difference ordered case, we know that this monad that we had before on sets actually lifts to a monad on partially ordered sets. I just think that's very pretty. This is like a nice condition, a sort of sufficient condition for this monad from before to lift to a monad on partially ordered sets. Okay, so yeah, this is one of the cases in which the construction that I suggested before actually does produce the free ordered P module. So some examples. Okay, well, The non-negative real numbers is certainly an example. It's certainly cancellative. And yeah, I mean, it's also difference ordered. I think we all kind of recognize that. So let's go through a couple of constructions of the actual free order P module. It's always going to construct the same set. Remember, in the cancellative difference ordered case, we just need to construct this set. We don't need to take any quotients or anything. We do receive an order in response to the construction, though. So here, if I just take the 3-element set 0, 1, 2, just discretely ordered, so I'm basically going to get the non-negative reals, positive vectors in R3 with the sort of component-wise order, right? Just the product order on the positive reals. I've drawn a picture here of like the upper set generated by some vector, sort of the positive cone from that vector. Now, if I sort of treat 0, 1, 2 as an ordinal instead, as like a linear order, then I get, I mean, it's the same set, but with a slightly different order now. The order is, it's given by these it's given by these sums, which I've just sort of directly pulled from the definition of the heavier higher order. These were those like bar graphs. You're looking at right-facing rays. Okay. Let's talk about the idempotent case, because this is another interesting case. So semi-ring is called idempotent if R plus R is equal to R. Basically, what sets these examples aside, and one of the things that we might find interesting about them is that any P module where P is an idempotent semi-ring is going to be a semi-lattice of sorts. You actually show that X plus X equals X in this case. Here's a famous example. So if you take P to be 2, so the 2-element ordered semi-ring, just ordinal 2, with the sort of normal usual operations, it actually turns out that the free semi-ring on the set X over 2, the free 2 module on a set is actually just the finite power set, like all the finite subsets. And if you mod this out by the heavier higher order, maybe you could guess this, maybe you didn't. It surprised me, not for any good reason. This is actually the same thing as the set of finitely generated downwards closed sets in the partial order. You might recognize this as like the free semi-lattice construction on a partial order. I mean, that's exactly what we're doing. This is like the free semi-lattice construction on a partial order. Yeah, and here I've just sort of written down the exact, like one example of this on the 3-element, like the ordinal 3. Okay. Now, unfortunately, in this case, that monad that we had before does not work. If you like monads, this is sort of another note for you. Just a few observations before I wrap up, because everyone likes a talk that goes quickly. These two cases I've considered are actually kind of orthogonal in a sense. So if I assume my semi-ring P is not only cancellative, but also idempotent, then that semi-ring is 0. There's only one ordered semi-ring that is both cancellative and idempotent. So I've kind of got two completely different directions going in this theorem. Another weird kind of feature of the examples I've considered before, or up until now, is that they're actually all difference ordered. So idempotency implies difference order. It's a very frustrating discovery because it means that maybe my original question was a little bit too broad. I've cooked up this horrible example of a cancellative ordered semi-ring that is not difference ordered. Maybe I'll go into more detail about this in a question period because I want to just sort of plug my last question in here. I'm working with this. I think it could be a counter, like it could be a negative answer to my original question. So I think that maybe a more reasonable question would be that, like, if you have a difference ordered, semi-ring, is the free ordered module over that semi-ring given by the construction before? Like, is difference ordered actually a necessary condition for this construction to work? yeah, I realize that's everything I had to say. Here's a few references. I'm not going to leave these up, but there's sort of an interesting history here. I mentioned at the beginning that the probability distributions on a set was a free algebra construction that was kind of like implicit in what I was saying. This goes back to Marshall Stone. It's like very interesting, but anyways, I'll take questions now. Thank you so much for coming.
That you cite this Bonki Sokolova in your daily paper and also in your abstract. So what's the relationship with the interaction of non-determinism and probability?
Okay. So in that paper, they talk a lot about monad presentations. In particular, they present the convex power set monad, but they also talk a lot about like presenting the finite probability distribution monad. I threw that in there because if you go and read the abstract, like my notion of monad presentation actually comes from that paper. And I think, that paper is like such an interesting exploration of monad presentations, especially in relation to the like machines I had at the beginning. That's mainly why I really like their notion of like presenting monads. It's really clean. Yeah. Here.
Do you have a sense of why this is, constructing the free object of the order base, why is it complicated? Because in universal algebra, you take the free term algebra and then you factor by something and you have the free object. So.
Oh, yeah. If you take the free term algebra and you mod out by the order, yeah, this does give you the free order.
But you want an explicit description of it.
Yeah, exactly. I don't know. That's a bit abstract for me. I really want to know what are the elements of it. And in particular, so I had this thing at the very beginning, this machine at the very beginning. Okay, I'll put it here. I want to be able to draw these pictures earnestly, And this kind of implies that this free ordered algebra is just like, if I look at X and I want to write down the term that corresponds to it, this actually is just a finally supported probability distribution. So I'm not encoding anything about the order in the actual notation here, other than the Hasse diagram, which seems to play no role in the definition of the automaton. So my answer is I want to be able to draw these pictures. That's really why I want this construction to work. Yeah. Yeah, I can go back to this. Any other questions? Yeah.
Just one place, I don't know whether you looked there or not, but in domain theory, there's quite a lot of work that has been done on like free algebras and probability theory, and also like these valuations, right? That show up in your. So that could be just a place to find inspiration or even results.
Yeah. Okay. That's a great suggestion. I feel like I looked at the domain theory literature a bit, but this could use. This really just.
Maybe I can also point you to some papers. I'm not a great expert in this, but I know that this has been like there's a whole thread of literature out there.
We should talk about this. Yeah, that's another thing about this question. Like I sort of scoured the literature because it seems like a question that it's not totally unnatural, but I really couldn't find a direct answer to this question. So, yeah, domain theory is a good place to look.
Okay, let's think of this figure again.